As you can see in our agenda here today, we're going to be taking a look at the requirements, constraints, and consumptions that go into a virtual infrastructure design. We'll be talking about the design deliverables that you will oftentimes see in a design engagement. And we'll talk about the major architectural components of a virtual infrastructure design.
In this webinar, we will be covering portions of a course called vSphere Design Workshop. For more information about this course and others from VMware, please go to vmware.com/education. Additionally, the topics that we'll be addressing in this webinar are covered by the VCAP DCD certification. That's the VMware Certified Advanced Professional Data Center Design certification. And again, if you go to vmware.com/certification, you get more information about that certification and others.
To begin, we're going to take a few moments to explore some of the general concepts that are involved in designing a vSphere virtual infrastructure. When designing a virtual infrastructure, there are a number of guidelines that architects will follow. The list here that we see on the screen is not intended to be a comprehensive list, but rather to be a list of bullet points for us to consider and to get us thinking in terms of design. So the first bullet points out that an architect is going to strive to eliminate single points of failure from the design. For instance, in the networking portion of the architecture, the architect is going to set up network connectivity between virtual machines, the hosts, and other components in the infrastructure. And one of the primary components that makes that possible is the physical NICs in the ESXi hosts. Now, another word for physical NIC in this case is VMNIC. Those VMNICs potentially represent a single point of failure. So in order to make certain that the networking doesn't fail due to the loss of a single NIC, an architect is going to design into the infrastructure multiple VMNICs to make certain that the otherwise catastrophic loss of network connectivity doesn't occur. The second bullet point here points out that the architect is presumably going to be working with the customer in the design to make certain that the architecture that's created is scalable. In other words, the design needs to support not just the customer's current needs, but the architecture needs to be able to grow along with the customer and be able to support more and more workloads, more and more virtual machines. Another consideration in design is making certain that the architecture itself can support maintenance activities. So for instance, if periodically the ESXi host and the environment need to be updated, if they need to be patched, an architecture can be designed to provide excess host capacity so that when patching is required, one or more hosts can be taken offline, patched, and then brought back into service without ever causing any disruption to the virtual machines that are running in that infrastructure. Again, the key thing that makes that possible is making certain that the design includes excess capacity in the ESXi hosts. Standards, in particular naming conventions, are oftentimes brought into the discussions about an architectural design. The reason being that these naming conventions, whether they're naming conventions for virtual machines or hosts, data stores, networks, those naming conventions ultimately make it easier to manage and operate the environment itself. So in a design engagement, it's fairly common to have a portion of that engagement addressing the various standards, in particular naming conventions that are used in the architecture. Addressing security is obviously an important point in a virtual infrastructure. In a virtual infrastructure, we want to make certain that those who are entitled to use the infrastructure are able to get to the various resources, the various virtual machines that they're supposed to have access to. And additionally, from a security perspective, we want to make certain that those who are not authorized are not able to get to entities and components and virtual machines that they're not supposed to have access to. The second to last bullet here points out that cost is oftentimes a key consideration in virtual architecture designs. You can come up with an architectural design that's the world's greatest design, has all the features, all the bells and whistles imaginable, but if that architecture is too costly to implement, then that obviously is going to jeopardize the virtualization project. So considering the costs involved, not just the physical hardware costs, but also the cost of the software components that go in to build a virtual infrastructure is a key part of coming up with an architecture that suits a particular customer. Now the last bullet here points out best practices. There are various technical best practices that VMware recommends in order to create and operate environments in an efficient and cost-effective way. And those best practices are intended to be followed in general. But as we'll see in the following slide, best practices are certainly to be considered in the design, but there's more to best practices than just simply accepting them at face value. So let's continue onwards here and see what that's about. When designing a virtual infrastructure, there are numerous trade-offs involved. And oftentimes what ends up happening in the designs is that these trade-offs need to be examined, and there ends up being at times a balancing act that you have to perform between the technical best practices as opposed to the goals and requirements and constraints of a particular customer organization. So while best practices are intended to be followed in general, there will be times when an architect identifies various aspects of the particular customer project that will warrant overriding the best practices. Now, when that's done, it's wise to actually document those instances where the best practices are being overwritten, and additionally to document not just that they were overridden, but what the rationale was behind doing so, and who the interested parties were that were involved in the discussions that led to that trade-off. Now, in designing, again, there are numerous trade-offs involved. The trade-offs between applying best practices versus tailoring the infrastructure to a particular customer organization's goals is one of the trade-offs, but there are numerous other trade-offs involved besides just those. So it ends up being a balancing act, and in order to perform that balancing act, the architect is going to need to work with the customer, in particular the key stakeholders and the subject matter experts, to make certain that the design choices that are being made make sense and that they're weighed against each other. Now, to explain that, let's go to the next slide and take a little deeper look. One of the design decisions that's going to need to be made in any virtual infrastructure is the number and the size of the ESXi hosts that are involved. And again, to sort of point out what some of the trade-offs are involved in decisions such as that, consider the following example. So suppose, for instance, an architect is working with a customer, and the architect and customer are working together to determine how many hosts and what size hosts they should use in the environment. Now, those hosts are going to be used, obviously, to run virtual machines, and various features such as HA, high availability, and DRS may be turned on to support the needs of the customer. Now, let's focus for a few moments specifically on vSphere HA. So if the choice is between having, for instance, 4 hosts versus 2 hosts, we could provide the same amount of host capacity by simply changing the configuration of those hosts. So for instance, we may choose to have 4 hosts, each equipped with 8 cores and 16 gigabytes of physical RAM. Alternatively, we could provide the same amount of host capacity but with 2 hosts, each being equipped with 16 cores and 32 gigabytes of RAM. So in both cases, whether we're running a 4 hosts or 2 hosts, in both cases we have 32 cores and 64 gigabytes of memory, but in the first instance, we have a larger number of hosts. In the second instance, we have a smaller number of hosts. So with the larger number of hosts, you'll notice that each of those hosts is smaller. So we have more hosts. We've got 4 hosts, but each of those hosts is smaller. On the other hand, in the 2-host configuration, we have fewer hosts, but they're each larger. And as a result, oftentimes you'll find, as you go out and price different physical servers, that the cost of providing more hosts, even though they're smaller, the cost of providing more hosts can outweigh the cost of providing fewer larger hosts. So for instance, in this particular hypothetical example, the 4-host configuration, the cost associated with that is Y. On the other hand, the 2-host configuration costs less. It's only 4/5 as much. Now, looking at this particular example so far, we can see that there's a trade-off involved. I mean, we can go one way or the other, and there's a cost differential between those two. But as we continue onwards, if we decide in the design process that we are going to turn on vSphere HA, that's going to have an implication. So in the case of the 4-host cluster, if we're going to reserve enough capacity to be able to restart virtual machines if a host fails, then we need to reserve 1/4 of the CPU and 1/4 of the memory capacity of each of those 4 hosts. So 25% of the resources have to be set aside in order to support vSphere HA. On the other hand, in the 2-host configuration, if we only have 2 hosts, if we want to make certain that we have enough excess capacity to restart all affected virtual machines if a host fails, if there's only 2 hosts, then we're going to have to reserve 1/2 of the capacity of each of those hosts, or 50% of the capacity of each host. So looking at this seemingly straightforward example here, it's a pretty simple example. The numbers here aren't that large, but it does point out that as an architect works with the customer to make decisions about things such as the number of hosts and what size, there can be numerous different aspects that factor into the decision that's being made. So while it may be tempting to just look at the list price of the servers involved and multiply it times the number of hosts, there can be other design decisions that will impact the overall cost of this infrastructure. So that's a quick look at just a single example of a trade-off involved in the design. But going back to design in general, the approach that the architect takes in performing a design engagement needs to utilize a methodology that's tried and true and can thoroughly investigate the needs of the customer, the requirements of the customer, and any constraints that the customer may have. Now, in order to be able to elicit from the customer the information that the architect needs to come up with the architecture that's tailored to that particular customer organization, it's very common for the architect to work with the key stakeholders and the subject matter experts within the customer organization in order to elicit that information. As the engagement proceeds, there is very likely going to be an interviewing process or design sessions in which those key stakeholders, the subject matter experts, and the architect sit down to discuss various aspects of the infrastructure, such as what are the desired performance characteristics, what level of availability, what degree of scalability is desired, along with other characteristics such as manageability, security, cost, compliance to regulatory compliance issues, and risks. But ultimately, when going through those design sessions and in designing the architecture itself, it's imperative that the architect create extensive and thorough documentation that explains not just the actual architecture itself, but the design decisions and the justifications behind those decisions. So as I said a few moments ago, in order to elicit the necessary information from a customer organization, the architect is going to conduct various design sessions with the subject matter experts and key stakeholders within the customer organization. Now, exactly what those design sessions look like can certainly vary from one architect to another, or even from one design engagement to another. But the sessions will typically involve potentially one-on-one interviews with the various key players in the project. The interviews could be conducted in person, they could be conducted over the phone. There may be whiteboarding sessions involved in which the architect and or the customer parties involved will actually design the infrastructure and consider in those whiteboard sessions some of the design trade-offs that we've been alluding to. But ultimately, the design is going to need to consider the various goals of the customer. Again, these design sessions are intended to elicit what those goals are. But in addition to the goals, customers have oftentimes very specific requirements that the architecture needs to satisfy. Additionally, customers will oftentimes have various constraints that the architecture needs to be in line with, and following those and along with the various guiding principles, the architect and the customer work together to come up with a design that fits their particular needs. So again, to provide solutions that work, it generally involves collaboration between the architect and the subject matter experts and key stakeholders within the customer organization. So those subject matter experts could be experts in various technologies such as storage versus networking. Other subject matter experts would include personnel that act as members of the server team or the operations teams. On the other hand, when we refer to key stakeholders, we're talking instead about people who are involved at the customer environment, whether those people be C-level executives or VPs or directors or even down to managers of different lines of business. The key stakeholders represent more the business side of the organization, as opposed to the subject matter experts are more the technical side. But as an architect, working in these types of design engagements involving all those different parties is an essential task. Okay, so now that we've taken a look at some of the general concepts involved in a design engagement, we're going to turn our attention now to the various requirements, constraints, and assumptions that customers have and which the architect factors into the virtual infrastructure architecture. Now, a few moments ago, I mentioned the notion of design sessions and how whether those were interviews or whiteboard sessions or whatever form the design sessions take form in, the point of those design sessions is to find out information about the customer's needs, to find out what their requirements are. What are the goals of the project? What sort of constraints does the customer need to place on the architect? And consequently, what constraints are there going to be on the design itself? Additionally, in a design engagement, there are oftentimes assumptions that have to be made. There may be various information that would be useful to have in coming up with the design, but for whatever reasons, there can at times be information that's not strictly known but has to be assumed. Now we'll take a look at requirements, constraints, and assumptions in more detail in the slides coming up. But this particular slide here is, again, just intended to get you thinking along the lines of what sorts of questions and issues get tackled in design engagements. So a design itself is not simply a piece of paper that the architect sits down and draws cool-looking pictures, but rather the design takes a lot of different information, potentially from a number of different sources, to come up with a design that fits for a particular customer. So for some customers, there are going to be business objectives that can be potentially very, very different from other customers. One example I've seen in the past, just to get us thinking along these lines, is I recall a number of years ago working with a customer. I was somewhat surprised when the customer mentioned that the consolidation ratio that they were striving for, consolidation ratio here is the number of virtual machines per host, was very, very low. In fact, the customer proudly proclaimed that they were only striving for a 1-to-1 consolidation ratio. Now, admittedly, this is a very unusual example, but what that particular customer was doing in their virtualization project was primarily focused on simply providing a disaster recovery capability that suited their needs. Now, there are a number of different ways that you can perform DR design. For instance, you could incorporate VMware's Site Recovery Manager, which is most certainly not limited to a 1-to-1 consolidation ratio. But that particular customer, to serve their particular needs, was perfectly satisfied with a 1-to-1 consolidation ratio. They weren't concerned about the cost savings. They weren't concerned about many of the things that most customers are. They just simply wanted to have a rock-solid way of doing DR for a subset of their machines. So that, again, I give that particular example as an example of a customer who had very different business objectives than most customers. So in the design sessions, the architect is working to find out what the objectives are. Additionally, in talking with the customer, it may turn out in the design sessions that the architect uncovers the fact that the customer is subject to various regulatory compliance standards, such as HIPAA or SOX or PCI. Depending upon what regulatory compliance issues are involved, that can have a fairly significant impact on the design itself. In coming up with the design itself, not just for the timing of the design part, but the actual implementation, it's important for the architect to understand what the schedule is for the project. It's also very useful for the architect in working with the customer to help identify if there are any training needs for the existing customer staff. Just because the virtual infrastructure is going to be a superb design that operates very, very well and is very manageable, it doesn't necessarily mean that the customer is staffed with employees who currently understand everything that they need to know about virtualization and the technologies involved in this architecture. So an architect can work with the customer to help identify who will be operating the infrastructure and what skills that they'll need in order to operate it, and then to perform a gap analysis to figure out what it's going to take to get those particular employees ramped up in their training and their knowledge, so that when the architecture rolls out, the necessary skills and knowledge are already present in the customer environment. Other issues, again, this is not intended as a comprehensive list, but other issues that the architects are going to be looking for are things such as, is this virtual infrastructure just a centralized design where there's just one data center, or perhaps there are multiple data centers or remote offices? It's possible that there may be organizational policies that affect the design. For instance, it's possible that there could be the need to separate virtual machine workloads based on departmental boundaries, for instance, sales versus research and development. The architects are going to work with the customer to find out what the security requirements are. And additionally, the architect is going to quite possibly run into various political issues within the customer environment that the architect needs to be sensitive to, and needs to make certain that the final architecture actually addresses those issues, whatever they may be. So again, this is not intended as a comprehensive list. In class, we talk about other issues that go into the design, but the key point of this particular slide is there are a lot of different considerations that go into a design. On the previous slide, we introduced the notion of requirements, constraints, and assumptions. So as the architect works with the customer, the architect needs to identify what are the requirements that the customer has for the new virtual infrastructure that's being designed. So those requirements could be business requirements, they could be technical requirements. As some examples we have here on the slide, it may be the case that this particular customer is subject to SOX regulations. So if Sarbanes-Oxley is an issue, the architect needs to identify that and to incorporate the necessary aspects of the design to remain compliant with SOX. Another potential requirement the customer may have would be an SLA that mandates a high level of uptime. For instance, their SLAs may indicate that a 4 nines of uptime is required. So 99.99% of the time this infrastructure has to be up during normal operations. So by identifying, for instance, the requirement for 4 nines of uptime, that's going to provide the architect the information necessary to make certain key decisions later on. For instance, one of the design decisions is going to involve that revolves around the uptime of virtual machines is the decision of whether to use vSphere HA versus VMware fault tolerance, or to use some combination of those. So if, for instance, the architect identified that a subset of the machines, the virtual machines that the customer plans on running, are business critical and can tolerate essentially no downtime at all. If for instance, there's a 5 nines SLA on certain virtual machines, then the architects are going to take that in consideration, and 5 nines SLA is not something that HA is going to be able to satisfy. The way HA works is to restart virtual machines that are affected when a host goes down abnormally. And the key word there is restart. If vSphere HA is going to restart virtual machines, then that alone, just one event could blow away your 5 nines SLA. So in the case of a 5 nines SLA, that's going to be a piece of information that's going to steer the architect to incorporate VMware's vSphere fault tolerance functionality into the environment. Whereas vSphere HA restarts virtual machines, in the case of host failure, with vSphere fault tolerance, if a host fails, the virtual machines that were running on that host continue to run with no downtime. So again, understanding what the requirements are helps the architect know what features and functionality he or she needs to build into the architecture itself. As I mentioned earlier, another thing that the architect is going to be working with the customer to identify is various assumptions that need to be made in order for the architectural work to be performed. There will be certain cases, hopefully not too many, but in a design engagement, there are times when the architect needs certain pieces of information that the customer may not be able to supply in a timely fashion, or in some cases, the customer may not be able to provide that information at all. And rather than completely derail the virtualization project entirely, the architect can identify what those pieces of information are that are missing. The architect and or the customer can come up with some educated estimate of what the answer should be, but to call it out as an assumption, so that in the design itself, by calling out the assumptions, we know that there were certain pieces of information that we didn't necessarily have when coming up with the design. So to give some examples here, it's quite possible, for instance, going with the second to last bullet here, it's quite possible in the design sessions that the architect and customer may identify that there are multiple data centers involved in the virtualization project, and that there needs to be network bandwidth between those with sufficient network bandwidth with low enough latency. And when the time comes for that discussion, that the architect is very likely going to ask, well, how big is the pipe between these two data centers? What is the bandwidth? What is the latency that we experience between these two different data centers? And at that point, in an ideal world, the customer will always tell you exactly the answer that you need to know as an architect. But in some cases, it may not be possible for the customer to answer that particular series of questions because the network connectivity between the data centers hasn't even been deployed just yet. So in situations like that where perhaps there's a bit of a chicken before the egg nature to it, instead of waiting indefinitely to find out what the network connectivity is, the architect can simply stipulate the assumption, we're going to operate on the assumption that the network connectivity between these two different data centers will provide X bandwidth with Y latency. But again, by calling out these assumptions, it helps to make all the parties involved aware that there are certain pieces of information that we're not necessarily in possession of, but that we're going to proceed forward with the design based on some educated, don't want to say guesswork, but in worst case scenario, educated guesswork as to what the answers would be. Again, assumptions allow us to call those issues out to make certain that everyone's aware, but allow us to continue onwards with the design engagement. In the meantime, if answers to the questions behind those assumptions come into play, then that can be worked into the design at a later stage of the design process. On the other hand, in some cases, there are assumptions that carry forward throughout an entire engagement, and you just have to work with the limited information that you have. Another thing that the architect's going to be working to do is to identify any constraints that the customer is placing upon the architect or the virtualization project itself. So for instance, it's possible that the customer is not going to allow the architect to pick exactly which make and model of physical server that will be used as the ESXi host platform. It's entirely possible that the customer already has an existing relationship with the server vendor. The customer is very happy working with that server vendor and intends to continue working with that server vendor. So if there are constraints of that sort, the architect works with the customer to identify what those are to make certain that the design doesn't fall outside of those constraints. And one more item that's listed here, we didn't call it out specifically before, but another thing that an architect is going to be looking for in a design engagement is any risks that may exist within the project itself or in the resulting architecture. So for instance, it may be that during the various design sessions that an architect has with the customer, it's possible that the architect may identify that the underlying networking infrastructure that's being provided is subject to a single point of failure. The architect, if the architect is primarily responsible for the virtual components and not so much in control of the networking components, the architect can spot issues such as a single point of failure router, point those out to the customer, and make them aware of the risk that's there, make them aware what the potential impact is if that risk is exposed during actual operations. So requirements, constraints, assumptions, and risks are some of the main things that an architect is looking for in the design sessions that we mentioned earlier. In the following slides, we're going to be taking a look at several, not necessarily all of them, but many of the main deliverables, the documents that tend to be produced in design engagements. Now, in different virtualization projects and different design engagements, it's very possible that the exact design documents that are presented to a customer are going to vary. So depending upon the type of project, depending upon the cost of the project, depending upon the timing of the project, the length of the project, there are a number of different things that can affect exactly which design deliverable documents an architect ultimately presents to the customer. Typically, whichever those deliverables are will be spelled out in advance in the statement of work for the project itself. But the key point of this particular slide is that different projects for different customers are not necessarily always going to end up resulting in the same exact documentation being presented. But what we're going to take a look in the following slides is what some of the common pieces of documentation are that are the result of these design engagements. One design deliverable that an architect may present to the customer in a design engagement is a capacity analysis report. There are various tools available to architects, such as VMware's Capacity Planner, which will go out into a customer's existing infrastructure and analyze the machines that they already have, looking at the capacity of those machines, looking at the utilization of those machines, looking at the performance characteristics of those machines. Tools such as Capacity Planner make it possible for the architect to find out information about what the customer currently has. That information can play a key pivotal role in coming up with the sizing of the virtual infrastructure. That information may be information that the architect analyzes and keeps to him or herself, or it is possible in some engagements that the architect will actually present the findings of those investigations to the customer. So a capacity analysis report may or may not be an output of a particular given design engagement, but it does oftentimes end up being presented to the customer. On the other hand, essentially every design engagement is going to have some sort of blueprint for the actual design itself. The blueprint will typically contain different levels. For instance, there's a physical design aspect of the blueprint, whereas the physical design gets very, very low level and talks, for instance, about specific components, both hardware and software components and the way things are configured. The physical design portion of the blueprint is very, very low level and points out information that's ultimately going to be required by the people who are implementing, deploying, and operating the environment itself. Now, there are other portions of the blueprint. For instance, there's a conceptual blueprint, there's a logical blueprint. Those are higher level views of the same architecture, but by remaining at that higher level, they provide different audiences the ability to see deeper and deeper into the design itself as necessary. And additionally, by having these different levels of design, that also provides a much more seamless transition throughout the design engagement itself. Instead of just jumping straight in and working on a low-level physical design, an architect's going to work initially with the customer to come up with a conceptual design, a much higher level view of the architecture. By working with that conceptual level design initially, that allows the higher level issues to be tackled without getting bogged down in the low level details of exactly which kind of host, exactly which kind of NIC, exactly what all the particulars are. So in those design documents, they're going to take a look at various aspects of the design itself, so not just the physical host, but the vCenter server, the cluster or clusters that are involved. There could be HA clusters, DRS clusters, clusters that have a combination of those. There's the network portion of the design, storage portion. As you can see here in the remaining bullets, there are a number of different aspects that get incorporated into the designs themselves. In some design engagements, the architect is going to produce a design verification document, which is a document that's intended to enable the customer, or in particular whoever's implementing the virtual infrastructure, to make certain that the design is functional and that the implementation is functional and working in accordance with the goals, requirements, and constraints that the customer initially placed on the architect. So that verification document is quite likely going to look into issues such as the customer may have high uptime needs, so building in redundancy into the console network is an essential component of a design. Customers very frequently have the need to have their network traffic segmented via VLANs. So the design verification document can talk about issues such as what the VLANs are, how they're to be set up, both in the physical infrastructure and in the virtual infrastructure. And as we can see in the remaining bullets here, there are additional areas. Once again, this is not intended as a comprehensive list. If you want a more comprehensive view of this particular subject matter, do come join us in class. But DRS, fault tolerance, HA, storage redundancy, and virtual machine restoration after failure, these are all various characteristics that can be touched upon by the design verification document. So by providing information about how to test the implementation of these different features, the architect's able to guide the customer to have an even higher degree of confidence in the resulting architecture. In the remainder of this webinar, we're going to be taking a look at the various major architectural components that go into a virtual infrastructure architecture. Various components go together to build a vSphere virtual infrastructure. These include storage infrastructure, network infrastructure, the vCenter server or servers, the SSO server, and various clustering technologies such as HA, DRS, and so forth. Now, we only have an hour here in this webinar, so obviously we can't go into each and every one of these, nor is this list a complete list. If you want more information than we provide here in the webinar, do consider attending the 3-day vSphere design workshop. But let's take a look at these different subject areas. And we're going to start with vCenter server. Again, storage and network is a pretty big subject in and of itself, so we're going to start with vCenter server. When designing an architecture for virtual infrastructure, there's going to be the need for a vCenter server, which, as I'm sure you know, acts as the central point of management for our whole virtual infrastructure. Now, with that vCenter server that will exist in your architecture, the vCenter server itself could utilize different versions that we have. There's a Windows-based version of vCenter server, and there's a Linux-based vCenter server virtual appliance. And depending upon what exactly the customer is trying to achieve and whether one or the other of those platforms better suits the customer's needs, the architect will steer the customer design towards one or the other. In terms of the machine that the vCenter server runs on, the machine, if it's a Windows-based vCenter server, the machine could run as a physical machine or it could be a virtual machine. On the other hand, the vCenter server virtual appliance, as its name implies, is not run as a physical machine, but rather a virtual machine. But regardless whether you choose the Windows version of vCenter or the virtual appliance version of vCenter, regardless whether you choose physical machine or virtual machine, they each have hardware requirements that you need to satisfy. And those are actually spelled out in the official product documentation. Those numbers change from release to release, so make certain that you're always checking the latest information. Now, when deciding between the vCenter server, which runs on top of Windows, or the vCenter server virtual appliance, both have been around for numerous years. The vCenter server on top of Windows platform is the older of the two technologies, but it's a proven technology, runs on top of 64-bit versions of Windows, and it can provide the vCenter services necessary all the way from a small infrastructure all the way up to enterprise-wide environments. The vCenter server that runs on top of Windows supports different databases, including Microsoft SQL Server, Oracle, and IBM DB2. On the other hand, the vCenter Server virtual appliance is based on top of Linux. It currently only supports the Oracle database as its choice. Now, for its internal database, if you choose to use the embedded database, that uses a Postgres database. So some of the differences that you will see about the vCenter Server virtual appliance are ones such as I just pointed out. It has less support for other databases. It's primarily focused around Oracle and Postgres SQL databases. The choice of databases could be a design consideration for a particular customer. Again, working with the customer in the design sessions, the architect, one thing I mentioned before is that the architect is going to strive to find out, in effect, who knows what within that organization and what sort of background that they have. One of the things that the architect can look for is what the customer's comfort level is with these different databases. So it's entirely possible that an architect may go into one customer and discover that they already have Microsoft SQL Server set up. They already have a long track record using it. They have a lot of experience and a lot of institutional awareness and operational practices built around Microsoft SQL Server. On the other hand, the same architect may, in a different design engagement, discover that that customer is an Oracle shop, and that's the database that they use. So one of the design considerations behind choosing vCenter Server on top of Windows versus the virtual appliance is the choice of database. If the customer already has made that choice in their own environment, the architect will oftentimes just go with the existing database that the customer already has and is already comfortable with. Another issue that may drive the decision between vCenter Server atop Windows versus the virtual appliance is the fact that the appliance does not support a couple of features that the Windows version does. For instance, one feature that's not supported by the virtual appliance is linked mode. Linked mode, as you probably already know, allows you to have up to 10 vCenter servers working together cooperatively so that no matter which vCenter server you log into, you can see the entire infrastructure. You can power on a virtual machine regardless which of those 10 virtual machines, which of those 10 vCenter servers it's on. So that type of functionality exists in the Windows version of vCenter, and if the customer needs that functionality specifically, then that again is going to be something that the architect is on the lookout for, and if he identifies linked mode is a need of the customer, then that's going to steer the architect specifically towards the Windows version of vCenter. So there are a few things about the vCenter Server virtual appliance that it doesn't do that the Windows version does. If those individual little things, such as the support for linked mode, doesn't matter to a customer that the architect is working with, then either version of vCenter can work equally well in their environment. So depending upon issues such as the ones that we've outlined or others that the architect may explore with the customer, the architect is going to decide between whether to use vCenter on top of Windows or on top of Linux in the virtual appliance. Another component that exists in vSphere environments is the vCenter SSO server, the single sign-on server. Now that single sign-on server provides for centralized authentication between different VMware components, such as authentication to the vCenter server and other products from VMware such as vRealize Orchestrator and vRealize Automation. By having a single sign-on server, we are able to centralize the authentication so that when a user logs into one of the VMware products, he's effectively logged into all the products and does not have to repeatedly log in again and again. Now the SSO server it is not intended to completely replace any directory servers that you may have. In fact, SSO is designed to work with existing directory services that you may already have, such as Active Directory or Open LDAP. So In designing an architecture, the architecture is going to include an SSO server, but the architect is going to work with the customer to identify what type of directory service they're already using. So if the customer is already using OpenLDAP, then the architect is likely to have SSO act as a front end to OpenLDAP, or if they're using Active Directory, then use Active Directory. The point, though, is that you need to have an SSO server. You will have an SSO server. The design consideration here is really more a question of what is going to be behind that SSO server. And typically, an architect is simply going to use whatever directory service the customer already has. One of the features that's available in most vSphere editions is vSphere HA. HA, I'm sure you know, stands for High Availability. vSphere HA is a technology that enables, amongst other things, enables virtual machines to be restarted automatically in the event of a host failure. Now, whether or not an architecture will make use of HA is typically going to be determined by the design sessions that we spoke about earlier. So when the architect works with the key stakeholders and the subject matter experts, if they identify that there are virtual machines that would benefit from the protective capabilities of vSphere HA, whether that's host failure protection or VM failure protection or application protection, HA can provide those different types of protection. So it basically boils down to a question of whether or not the customer needs it. Now, unlike other features such as DRS, vSphere HA is more widely available throughout the different vSphere editions. In a few moments, I'll show you a document that shows you what features are in each edition. But most environments will benefit from vSphere HA, partly because most editions include HA, and additionally, having HA in a customer environment allows the more smooth recovery from failures which may eventually occur. A physical server that ESXi is running on may fail one day. Rather than having to scramble to identify which virtual machines were knocked out of commission if a host went down and manually restarting them all, instead of doing that as a very manual process by having vSphere HA in the design, customers can be much more confident that if a problem of that sort should occur, that the infrastructure will effectively heal itself. Now, if you are going to use vSphere HA, much like other technologies, if you're going to use vSphere HA, that's going to require certain underlying capabilities of your network and storage infrastructure. In particular, HA requires shared storage. So if the architect and the customer decide that HA is to be a part of the architectural design, then the decision to implement HA is going to necessitate building into the network portion and the storage portion of the architecture the capabilities that HA needs. And additionally, as the architect and customer goes through that decision process, deciding to use HA or other clustering technologies such as DRS oftentimes acts as a jumping off point to discuss whether or not certain other additional features such as distributed virtual switches could be useful in the design. Now, distributed virtual switches and other features aren't available in all vSphere editions. So let's take a few moments here and see, for instance, where vSphere HA is available as opposed to vSphere DRS. When creating clusters in the VMware vSphere environment, one of the design considerations that an architect will go through is whether to use a scale-up approach or a scale-out approach. So a scale-up approach involves a cluster that has fewer hosts, but each of those hosts is larger. On the other hand, in a scale-out architecture, the cluster is composed of more hosts, but they're each smaller. So if you want to think of it visually, scaling up, we're building bigger and bigger, taller machines, as opposed to scale out, we're building more and more and more capacity by having more hosts within our cluster. Now, when deciding between a scale up or a scale out architecture for the cluster, I mean, a big part of that decision oftentimes boils down to the costs involved. Now, there's not just the cost of the machines itself, but also consider into the cost considerations the impact that larger and larger clusters have on the manageability of the infrastructure. The more hosts there are in a cluster, the more administrative staff you need in order to manage that infrastructure, that cluster. So whereas a scale-out cluster may enable you to purchase more, less expensive machines, as a trade-off, it's quite possible that by having more machines, more physical servers acting as hosts, that you trade one cost, the cost of the machine, for another cost, which is the cost of the staff necessary to operate all those machines. Other things that will steer you towards scale-up versus scale-out are includes the purpose of the cluster. For instance, in some customer environments, they'll actually have two separate clusters. One that's a cluster for the virtual machines that are effectively running as virtualized servers, as opposed to another cluster that's used for the virtual machines that are acting as virtual desktops. So for instance, if a customer is implementing a virtual desktop infrastructure solution, having those different types of clusters allows the architect to build the cluster in a purpose-ready configuration. There are configuration aspects of a cluster for virtual servers that are different from what you do for a cluster of virtual desktop machines. By having separate clusters, you can design each cluster for the purpose that it's intended for. So short version of that, a VDI, a VMware View Type cluster, will typically be a scale-up type approach in which there's fewer hosts, but they're bigger. Again, doing it that way just tends to, not in every single case, but tends to make the cost more efficient in a VDI type environment. So on the previous slide, we talked about briefly about scale up versus scale out. In these slides, we're just going to go into a bit more detail. So with scale up clusters, again, recall a scale up cluster is when you have fewer larger hosts. So there's, one of the key advantages of a scale up design is that there's fewer hosts, which potentially reduces the cost of the physical hardware itself, but it also can have a significant impact on the cost for the staff that's necessary to manage and operate the cluster. On the other hand, with scale-up clusters, there are some potential disadvantages. So for instance, if you have a scale-up cluster, you have fewer hosts, and therefore you're likely packing more virtual machines per host. You have a higher consolidation ratio. So if you lose a host in a scale-up cluster design, the failure of that host with its more virtual machines is likely to have a larger impact. Now we know that with technologies such as vSphere HA and vSphere fault tolerance that we can either minimize or eliminate the impact, but in a scale-up cluster, a host failure tends to be a more significant event than in a scale-out cluster. Additionally, when you are doing a scale-up type approach, if you're turning on things such as HA, in a few moments we'll be talking about failover policies that HA has. In a scale-up cluster, turning on HA and setting that failover policy can have a significant impact on how much CPU and memory resources we have to reserve across the host in the scale-up cluster. In a scale-up cluster, again, there's fewer hosts, but they're each larger, and consequently, if we are scaling up, the architect needs to pay close attention to things such as the maximum number of virtual machines that can run on a host, or the maximum amount of memory that we can put in a host. All sorts of information along those lines is available in the vSphere Configurations Maximums Guide, which all architects will be familiar with. Whether you're doing a scale-up cluster or scale-out cluster, the Configurations Maximums Guide provides the maximum supported limits for various aspects of your virtual infrastructure, and it's imperative that the architect is aware of that document and knows how to comply with the maximums that it states. On the other hand, if you create a scale-out cluster design, there are certain advantages to scale-out and certain disadvantages. For instance, with a scale-out cluster, again, recall scale-out, we have more hosts, but the hosts are generally smaller and therefore run fewer virtual machines. In a scale-out cluster design, the loss of a host, if a host goes down, tends to have less impact on the environment because, first of all, fewer virtual machines are involved, and secondly, because there are fewer machines to restart, the restart that HA performs is generally faster for scale-out cluster designs. Additionally, fewer resources are required for HA, a lesser amount of CPU and memory is required in a scale-out design because the more hosts you have in a cluster, the less resource we have to reserve per host. On the other hand, unlike scale up, you don't have to spend as much time, the architect doesn't have to spend so much time and effort and attention to whether they're staying within the maximums that we talked about before. There still are configurations maximums that apply here, but it tends to be a little easier in scale-out clusters. The biggest issue with scale-out clusters to be aware of is to make certain that since the hosts are smaller, that you're going to be able to run large enough virtual machines on your smaller hosts. Another advantage of scale-out clusters is that if a cluster is a DRS cluster, the more hosts there are in the cluster, the more possible choices DRS can choose from as it strives to optimize the placement of virtual machines in your cluster. So with a scale-out cluster, you have more hosts. With more hosts, DRS has more choices, and with more choices, DRS can do a better placement. On the flip side, though, with scale-out clusters, there are downsides to scale-out clusters. So with smaller hosts, you are therefore not going to be able to run as large of a virtual machine. If a virtual machine is larger than the host can accommodate by virtue of being a scale-out design, that is one potential disadvantage. Another potentially significant disadvantage of scale-out is that because you're going to have more hosts, it's quite possible that you're going to need more data center space. It's possible that the cooling costs and the powering costs will be higher. And additionally, because there are more hosts, the cost of the staff required to operate the cluster may be higher too. So in general, there's no right solution that's going to fit everyone. Some customers will do better to have a scale-up design for their clusters. Other customers will do better with scale-out. Again, in the design sessions, the architect can work with the customer to figure out which sort of design will work better for that particular customer environment. For vSphere HA to be able to restart virtual machines in the event of a host failure, vSphere HA must reserve capacity from the hosts in the HA cluster. Specifically, HA needs to reserve CPU and memory resources. The mechanism in vSphere HA that sees to it that we reserve that capacity is a mechanism called admission control. And as you can see here, we have a screenshot from the Create HA cluster wizard. And in the screenshot, you can see that you actually have the ability to turn on or off this admission control capability. But as this slide points out, you should always have admission control enabled. If you disable admission control in an HA cluster, you are effectively telling HA that it does not have to reserve the capacity necessary in order to restart virtual machines in the event of a failure, which is not what you want. If you're running HA, presumably you're running HA so that you'll have assurance that if there is a host failure, you'll have the resources. If you choose disable here, you may not have the resources. So always choose enable. So moving onwards here, let's assume that we are going to enable admission control. Since we have admission control enabled, we're actually going to be given 3 choices in this HA cluster to guide HA in terms of how it should reserve the CPU and memory resources that it needs. As you can see here, the 3 choices are called the host failures, the cluster tolerates policy, the percentage of cluster resources reserved policy, and the specify failover host policy. Now, this is a point of architectural consideration. Again, we have 3 different choices, and depending upon what the customer needs, the architect is going to select one of these. Working my way backwards through this list here, on the bottom of the list we have a choice in which we can tell HA that we're going to specify hosts that will act as failover hosts. In other words, in our HA cluster, we're going to identify one or potentially multiple hosts that are effectively in standby mode, just awaiting a failure to occur. If a host fails in the cluster, then the virtual machines that were affected by that outage will get restarted on the failover hosts. Now, for most customers, this last choice, specify failover hosts, is probably not the choice that you want, because whereas HA can effectively act as in a active-active mode, here what we would be specifying with the third policy is that we want to have a portion of our cluster in a passive mode, where it's just where the hosts are just sitting there waiting for a failure to occur. Now, obviously, having hosts sitting there just waiting for failures is not generally going to be the most cost-effective way to configure your HA cluster. So unless there's a compelling reason that the architect and the customer identifies to choose this third option, in general, you won't choose the third option. The typical place or typical situation where a customer will choose to have failover hosts is if there's some sort of corporate or regulatory compliance issue that stipulates that we have to know where virtual machines are running at all times. In a HA cluster where we're not using this third policy, virtual machines could end up running on different physical servers. And again, for corporate reasons or regulatory reasons, that may be an issue. So in that particular case, that's a use case for the third policy. But most customers are going to actually choose between the first and the second policy that we see listed here. The first policy tends to work best if the virtual machines in your environment all tend to be roughly the same size in terms of their CPU and memory reservations. If the machines are not similarly sized, you can still use this first policy, but doing so and making use of HA in a cost-effective manner with the first policy essentially would mean that you would have to set some advanced options. If you go to a site such as www.yellow-bricks.com, you can see guiding information about how to set those advanced policies. On the other hand, many customers simply choose to go with the second policy, in which a certain percentage of CPU and memory is reserved on each host as the way of reserving the excess capacity that we need. So the second option tends to be used by customers because it provides a fairly simple strategy for reserving the capacity. And that second option tends to work very, very well in situations where the virtual machines in your infrastructure are widely divergent in their sizes. Now, one of the things I haven't said about HA so far in this discussion is how HA works. At its essence, the way HA knows if a host has failed is through a heartbeat mechanism. In older versions of vSphere, back in the days of before vSphere 5, there was one type of heart beating mechanism, which was a network heartbeat. The hosts in an HA cluster would send a message to each other through a network heartbeat. In vSphere 5 and above, we actually have the traditional network heartbeats. The traditional network heartbeats are still used to detect if there's a host failure. But in addition to network heartbeats, vSphere 5, HA, and above supports another type of heartbeat, a complementary type of heartbeat known as a data store heartbeat. Now, regardless whether you are using network heartbeats and or data store heartbeats, in order to avoid false positives, in other words, in order to avoid thinking that a host is down when it's not actually down, a strong component of a good architectural design will involve making the heartbeat mechanisms redundant. Now, as we can already tell just from the discussion so far, there already is a natural redundancy that's built in by virtue of using both network heartbeats and data store heartbeats. In an environment where the HA cluster is using both network heartbeats and data store heartbeats, it's going to be pretty hard to have a false positive, because in order for us to think a host that's not really down is actually down, we would have to have a failure of both the network through which network heartbeats are sent and the storage infrastructure through which our storage heartbeats are sent, which is pretty unlikely. But both data store heartbeats and network heartbeats can individually be set up to build into each of them additional redundancy. And in the following slide, we'll take a look at specifically, not the next slide, but in slides coming up, we'll be taking a look at the various choices, the architectural choices that you have if you're going to strive to have redundant heartbeat network functionality. So as I said a few moments ago, one of the heartbeat capabilities in vSphere 5 and above in HA is a data store heartbeat. Effectively, the way the data store heartbeat mechanism works is each host knows about a collection of data stores that they've agreed upon, in which each host is going to make use of a fairly small area of the disk, just 3 megabytes. And in that area of the disk, each host is going to write out information to indicate that it is still alive. So each of the hosts go out to potentially multiple data stores to record a little message to the other host to say, I'm still alive. Now, vCenter Server can select which data stores to do the heart beating on for you automatically, or you can actually specify it manually. Again, we're now venturing into some decisions that the architect needs to make. So is the selection of data stores going to be automatic, or is this something that we're going to manually configure? For instance, you might choose to manually configure data store heartbeats to avoid having data stores that make use of iSCSI. Since your iSCSI data stores could very well use the same network infrastructure that the heartbeat network uses, in order to keep the data store heartbeat and the network heartbeat separate, you may opt to manually select things other than iSCSI or NFS or other IP storage-based storage. The vCenter Server, when it selects the data stores in an automatic fashion, has various guidelines that it follows in order to pick the preferred set of data stores. So for instance, it's going to strive first and foremost to pick a collection of data stores that are seen by the most hosts in the cluster. We in general want the data stores that are being used for data store heartbeats to be visible by all of the hosts. And in many configurations that will actually be achievable. But in some customer environments, you may have some hosts that can see a data store and others that can't. By picking the data stores that are visible by the most hosts, we're striving to make the data store heartbeat mechanism as resilient as possible by making it visible by as many hosts as possible. The automatic selection of data stores prefers VMFS data stores over NFS data stores. Again, an NFS data store is a form of IP storage, and since it's IP storage, it could be using the same heartbeat network, the same network the heartbeat network is using. So by preferring VMFS over NFS, it helps to steer us away from a possible single point of failure in the underlying network. The automatic selection of data stores also seeks out to identify and make use of data stores that are actually backed by different storage arrays. Again, that's an automatic mechanism that's in place to help us avoid having any sort of single point of failure in terms of the data store heartbeat mechanism. As we can see in the last two bullets on the slide here, as I mentioned before, the heartbeat section of the data stores is by today's standards, is a very small area of the disk. The amount of space that's required for the data store heartbeats and the amount of overhead that's placed on the data stores and the overall I/O bandwidth that's consumed are all very negligible. So when coming up with the architectural design for a virtual infrastructure, an architect isn't going to spend a whole lot of time thinking about the amount of space that's required or the amount of bandwidth that's required for doing data store heartbeats, because again, those are negligible. What the architect is going to be spending their time thinking about is how to see to it that the data store heartbeating is going to provide the most surefire way of detecting if a host has failed while avoiding any false positives. So in the previous slide, we talked about how the data store heartbeat mechanism provides us the ability to detect host failures. But as I mentioned earlier, there's also a network heartbeat capability. And to use the network heartbeat capability, you could actually implement that network heartbeating in a singular fashion in which you only have one VM kernel port riding on top of one virtual switch riding on top of one VM NIC going out to one physical switch out to one network. If you detected there, I kept using the number one like one single point of failure. You can design a heartbeat network that has a single point of failure in it. In fact, you can have multiple single points of failure, but that wouldn't be a particularly sophisticated design. A more sophisticated design is going to have leverage generally one of two different approaches to make the heartbeat network redundant. One way of doing that is through the vSphere NIC teaming capability, in which a single virtual switch has two or more physical NICs that each connect to physical switches and ultimately get us out to the network. This design is sufficient in terms of providing redundancy of the heartbeat network, but it does leave the network itself as a single point of failure. So as you can see in the diagram here, yes, we may have multiple physical switches, we may have multiple physical NICs, multiple VM NICs, but ultimately, if those are all going to the same network, if the network goes down, then all the redundancy that we provided could be circumvented. On the other hand, in the following slide, we'll see how a little bit more work in the network design can provide a even more surefire way of detecting failures while avoiding false positives. So as you take a look at this particular example here, it looks very much like the diagram that we saw a few moments ago, but there are a few key things that are different here. The first thing that you'll notice if we go from top to bottom is that instead of having just a single VM kernel port called VMK0, in this design we actually have multiple VM kernel ports. So as a result, the VM kernel ports themselves are no longer single points of failure. Those VM kernel ports can each connect to separate virtual switches, again, thereby eliminating a potential single point of failure. And each of those virtual switches can have their own dedicated physical NIC. So again, eliminating single point of failure. As you look further and further down in this particular diagram, the key thing to notice in this second design is that we're actually plugging into two completely separate networks in this case, which means that all the heart beating that's being sent can continue to function even if one of these networks goes down entirely. Now, if we lose both networks simultaneously, that's a different issue, but this design here provides for a greater degree of resiliency, a greater degree of being able to continue to provide the heart beating capability even if we're losing components of our network. Now, changing gears here, let's look for a few moments at Distributed Resource Scheduler, or DRS. As we pointed out earlier, DRS is a feature that's only available in vSphere Enterprise Plus. As you see on the slide here, in general, we recommend turning on DRS wherever possible, but obviously with DRS existing only in the Enterprise Plus edition of vSphere, that is going to narrow down the number of customers who actually have DRS as an option. So when choosing to use DRS or not, in general, yes, we want to use DRS. It's not a question of does the technology fit for one customer or another. DRS will generally work with all customers. The architectural design decision here at this point isn't really about the technology, but rather about, is this a technology that the customer needs and which fits within the customer's budget. So again, in the design sessions, the architect can work with the customer to talk with them about what DRS does and what it's going to require, not just in terms of the licensing requirements, but the underlying hardware. But assuming that the customer does choose to go with DRS, the choice to use DRS will necessitate using an Enterprise Plus license. If DRS alone is not enough reason to warrant going to Enterprise Plus, there are a lot of other features in Enterprise Plus, such as host profiles and distributed virtual switches, which collectively could provide the justification for the Enterprise Plus license. So assuming a customer is going to make use of DRS, then one of the things that the design of the architecture needs to satisfy is DRS uses vMotion. So therefore, the design needs to provide all of the capabilities that are necessary with vMotion. For instance, vMotion historically requires shared storage between the hosts in the DRS cluster. Now that's been changing a bit over the years in some ways. For instance, vMotion historically required shared storage, but enhanced vMotion does not require shared storage. However, with vSphere 5, even though there is no longer a requirement for shared storage if you're using enhanced vMotion, DRS itself does not use that enhanced vMotion capability in vSphere 5. So in coming up with the design, if anything, that this little brief discussion here should point out that the simple version of this is you need to make certain that you satisfy vMotion requirements. The more complicated part of this is to recognize that in different versions of vSphere over the years, the landscape has been changing in terms of what vMotion requires and is potentially going to ultimately result in DRS loosening its requirements. But as of today with vSphere 5, you need to have shared storage in order to do the vMotions that are necessary to do DRS. In designing your cluster, in order to promote the compatibility, the CPU compatibility across the different hosts in the environment, one way of doing that is to simply purchase hosts that are identical with identical CPUs. In doing so, you can guarantee that, at least in the beginning, the CPUs in those hosts will be compatible and therefore vMotion and DRS will work. But in many customer environments, if not most, if hosts get added to the cluster sometime down the line, it potentially gets harder and harder to continue purchasing servers with CPUs that are compatible. Now, one way of dealing with that in the long run, or just right up front, is to turn on enhanced vMotion compatibility in your DRS cluster. So EVC is a sub-feature of a DRS cluster that arranges to have the hosts in a DRS cluster present an identical set of CPU instructions and CPU features in order to promote the vMotion capabilities that we need. Turning on EVC is not particularly hard to do. You simply turn it on and specify which generation of CPUs you want to have EVC present. When you turn on EVC, there's a KB article, a knowledge base article that's mentioned in the wizard itself that will explain to you what the difference is between those different generations. So EVC tends to be a very easy feature to turn on, and it's generally recommended because it has negligible impact on your cluster and makes the ongoing functionality of your cluster easier to manage. When designing a DRS cluster, one of the choices that you have is to put the cluster into a fully automated mode, a partially automated mode, or a manual mode. Now, ultimately, we generally steer our customers towards turning on that full degree of automation so that the DRS cluster can continuously rebalance the virtual machines across the hosts to provide for better performance across the overall cluster. Additionally, you can set different thresholds for how aggressive DRS is. In general, we recommend that the default migration threshold be used, but that full automation be turned on. Now, for some customers may have some sensitivity to virtual machines moving around without some sort of human involved in approving that. Again, that's why we have both the manual automation level and the partial automated level. You can drive your cluster down into those lower levels of automation all the way down to manual, which means that DRS will make recommendations, but you have to approve them. But rather than take that drastic move of leaving full automation mode and going to one of the lesser modes, an architect is very likely going to work with the customer to identify which virtual machines in particular are you concerned about moving around. For instance, a customer may be concerned with having the vCenter server virtual machine move around. Rather than turn on a lesser level of DRS automation, the architect can work with the customer to identify those virtual machines, and in DRS set up rules that say specific virtual machines are not allowed to move at all, such as the vCenter server, or there are other variations on that theme. Instead of saying a virtual machine is not allowed to move at all, you can say it's allowed to move, but I have to approve it. So part of the DRS portion of a design needs to take these things into consideration to figure out what's going to be best for this particular customer. While in general we say full automation, just go with the defaults, there are design considerations and customer considerations that need to be factored in too. The last bullet on this slide points out something that we touched on earlier, which is that the more hosts that you have in a cluster, which you typically see in a scale-out cluster, the more hosts that there are in a cluster, the more choices DRS has in terms of where it places virtual machines in that cluster. More choices generally leads to DRS being able to make better choices and to optimize more optimally the placement of virtual machines in your environment. One of the features that's available in a DRS cluster is the DRS affinity and anti-affinity rules. Now, before we can explain what these affinity and anti-affinity rules are, let's just get the following point out of the way, because it's probably the most important thing here. In setting up either of these types of rules, the rules themselves should be the exception. The more of these rules that you set up, the less choices you give DRS. The more rules you have, the fewer choices DRS has. The fewer choices DRS has, the less DRS is going to be able to do to optimize the placement of the VMs in your environment. So we're not saying don't do these rules, or we're not saying that these rules are broken or that they're bad, but in order to give DRS maximal flexibility in terms of workload placement, you should make these rules exceptional, not the norm. So what are these rules? An affinity rule instructs DRS that certain virtual machines that you identify should be kept together on the same host. On the other hand, anti-affinity rules do just the opposite. Anti-affinity rules allow us to specify a collection of VMs that should be kept apart, VMs that should be placed on separate hosts. In general, affinity rules are used for optimization purposes. On the other hand, anti-affinity rules are typically used for availability reasons. So, as an example of an affinity rule, if you have a collection of virtual machines that are perhaps implementing a three-tier application, so for instance, one of the virtual machines may be your database, the second VM may be your application tier, and the third, or perhaps even more, VMs are your web VMs. In a three-tier configuration like that, the machines involved tend to spend a good portion of their time communicating between those machines. Now, whether those machines are on the same host or different hosts, we can set up the networking to allow those machines to communicate with each other. But if we place all those machines onto the same host, then the network communication that's taking place does not have to go out to the physical wire, which means that the networking can stay within the host so that those machines can communicate with each other in the host. The networking is faster. Not only does this make the networking faster for these particular machines because their network I/O is being kept internal to a host, the fact that their I/O is being kept internal to a host is actually good for other things that are using the physical network. If these VMs, through an affinity rule, are being kept on this same host, they're generally going to run faster for themselves, and they're going to have less impact on other machines elsewhere in your infrastructure. On the other hand, anti-affinity rules, as I said a few moments ago, are generally used for availability purposes. So for instance, if you imagine the following scenario, you might be virtualizing your domain controllers. So multiple virtual machines, each is acting as a domain controller. As long as we have one domain controller, we can be up and running, but if we lose them all, we have no domain controller services. By setting up an anti-affinity rule, you can instruct DRS that it's okay to move these VMs, these virtualized domain controller VMs around, but you need to keep them on separate hosts. That way, if we lose a host, and as a result lose one of those virtual domain controllers, we're not in an ideal situation. We should fix the problem as quickly as we can. But the fact that we had an anti-affinity rule set up will mean that there will be at least another virtualized domain controller on another host that's still up and functioning. So affinity rules for optimization of network traffic, anti-affinity rules for availability purposes. Those aren't the only potential uses for affinity and anti-affinity rules, but those are two very common use cases. So we've talked about HA clusters and DRS clusters briefly here in this webinar. One of the things that you can do is you can certainly deploy those types of clusters separately. You don't have to. DRS and HA are designed to work together in the same cluster, but in some customer situations it may make sense to have a separate HA cluster and a separate DRS cluster. So that's one reason that a design may have multiple clusters. Other reasons may be by having a single cluster, you are more likely to hit some of those configuration maximums that I alluded to before. So by breaking up one large cluster into multiple smaller clusters, you can potentially work around some of the limits that are stated in the configurations maximums guide. Another issue that I alluded to before is that you may want to have separate clusters if you're doing virtual servers and virtual desktop machines. Again, for architectural reasons we don't have time to go into here in the webinar, it can be advantageous to have your virtualized servers in one cluster and your virtual desktop machines in another cluster. Let's see, so that's 3 reasons so far. A 4th reason for having multiple clusters is in larger environments, it's not uncommon to see a cluster that exists called the management cluster. And typically that management cluster will be a cluster that has both HA and DRS turned on, and the VMs that reside in that management cluster are essentially the infrastructure type machines that are necessary to make your virtual infrastructure work. So things such as domain controllers, things such as your Active Directory or Open LDAP server, things such as your vCenter server, and so forth. Those types of services, along with DNS and DHCP and so forth, those types of services in larger environments tend to be placed into virtual machines that are in a separate management cluster in order to provide a cleaner separation between the VMs that are providing the management capabilities of the infrastructure as opposed to the VMs that are being used by end users. So there can be a variety of reasons to deploy multiple clusters, but the number of clusters is yet another architectural decision that an architect working with the customer in design sessions and interviews and whiteboarding sessions, this is yet another thing for the architect to consider in the design. On this slide here, we have a few additional clustering technologies that an architect will want to consider when developing a virtual infrastructure architecture. The first one that we see listed here is DPM, Distributed Power Management, which is a sub-feature of DRS. If you have a DRS cluster, you can turn on DPM. And what DPM does for you is to optimize the power consumption in your environment dynamically. So when the demand from virtual machines for resources is low, DPM can place some of your hosts into standby mode, and then when the demand grows, DPM can automatically power on enough hosts to run the virtual machines that you need to run. So dynamic power management allows you to potentially save on power and cooling costs, and it also allows you to automate energy management in your data center much more efficiently than just having all your hosts powered on all the time. Another type of clustering capability that vSphere provides is vSAN, or virtual SAN. So with vSAN, we provide hypervisor converged storage that's designed and optimized for vSphere environments. It takes the local storage from your hosts that reside in a vSAN cluster. It takes that local storage and pools it together to create a effectively shared data storage capability. Now in vSphere 5, the vSAN capabilities that we provided allowed you to take a combination of hard disk drives, traditional hard disk drives, and solid state drives, and combine those together in that pool to provide highly available distributed storage. In vSphere 6, vSAN has been enhanced. It can still do a combination of hard drive and solid state drives like vSphere 5 did, but in vSphere 6, vSAN also has an all-flash architectural capability that allows us to provide data persistence on SSDs to provide and deliver extremely high performance with consistently fast response times. So again, in vSphere 6 vSAN, you still have the old choice of hard disk drive and solid state drive, or you can go all solid state drive. An hour-long webinar provides only so much time to talk about the various architectural topics that we've been addressing here. The design workshop that I mentioned before is actually a 3-day course and goes into much more detail about the issues that we've been tackling, plus additional topics that we simply had no time to talk about in this webinar at all. So we encourage you, if you are interested in the topic of design, there are a number of different resources that are available to you, including the classes that you see listed on the screen here. The design workshop is dedicated just to design. The Optimize and Scale class could be of interest to you to learn about some of the advanced features that we've been talking about, such as the various flavors of DRS and vSAN and so forth. So if you'd like to know more about any of our courses, please feel free to contact us at the toll-free number listed on the screen. Be sure to mark your calendars for April 15th. That's when our next webinar will be held. It will be led by my colleague, Jamie Rawson, and the subject for the next webinar is going to be troubleshooting strategies for vSphere 6. So do take a look in your email. There'll be registration details in the follow-on email that we'll be sending you. And as a collection of a few other resources that you may want to consider looking at, if you go to www.vmware.com/go/try-now, you can actually get hands-on experience with the various VMware products and technologies. So don't have to set up your own lab environment just to test out these technologies. You can go to vmware.com/go/try-now and take a look at them right now today. Additionally, you can use the various blogs from VMware, such as the ones that you see listed here on the screen, to keep informed of what's going on with VMware and our technologies and our training. The communities at communities.vmware.com provide a collection of discussion groups that discuss all sorts of different products and technologies from VMware. And last but not least, for informational and troubleshooting purposes, VMware's knowledge base at kb.vmware.com provides a wealth of information. Thank you very much for attending this particular webinar. And again, we look forward to seeing you at the next webinar on April 15th. Thank you.